If we want to know how much water flows out of the right arm, what we really want to figure out how much water is going to be displaced by the addition of this less dense fluid on the left side of the tube. Now, I first want to point out that a common mistake on this problem is assuming that the amount of water that is pushed out of the right side is going to be the same volume as the volume of fluid that is poured into the left arm of the tube. This is not the case, because since the left fluid is less dense, it's not going to be displacing the water that much, since the water is denser. What we really want to do for this problem is kind of think of it sort of in terms of Pascal's law, where instead of thinking of it in terms of how much volume of fluid we're adding, instead we'll think of the pressure. However much pressure we're adding to the fluid on the left side is going to come out on the right side as well, since the pressure is equally transferred. So how we really want to think of it is that however much pressure is changing on the left side is going to change equally on the right side, and we can use that pressure change to figure out the volume, or just the height, of the water that the right side is going to be raised by. So I'm going to use this simple formula, the formula that tells us a pressure difference between two heights, or a change in pressure. So however much we change the pressure in on the left side, that same change in pressure will happen on the right. So this is the full equation I've set up here, where the pressure being added to the left side is equal to the pressure being added to the right side. The only difference is the variables are going to be slightly different, because whereas g is constant and always stays the same, the density on the right side, I've used a little subscript w to represent that this is the density of the water, and this is the height that just the water changes by. If we want to find the volume change of the water, then first let's solve for the height of the water, then we can use geometry to solve for the volume. And so, dividing both sides of the equation by rho sub w, the density of the water, we can see that the height by which the water increases, or wants to increase before spilling out, is equal to the density of the lighter fluid times the height, h, of the lighter fluid we put in, divided by rho sub w, the density of the water. Now the problem is asking us for a volume of water that pours out, so we'll also want to come up with a relationship between the volume of the water and the height. We can just use this common geometry equation where the volume of a cylinder is equal to pi times the radius squared times the height, which in this case is going to be h sub w, the height of the water that's being raised. So we can substitute the first equation we solved into h sub w, and now we have this equation here, which will be the final equation we want to use. We have the radius of the tube, 1.5 centimeters. We have the density of the fluid, 0.8 grams per cubic centimeter. And for the density of water, we can just use 0.998 grams per cubic centimeter. Or just 0.1 grams per cubic centimeter if you don't want to deal with the decimal places. And for h, we'll just use 8.0 centimeters, since that's the height of the fluid, the less dense fluid that's added. And if you plug this into your calculator, you get a volume of 45.3 cubic centimeters. Now this is the amount of water that is going to raise on the right side in terms of volume, which means all that water is going to spill out, and this is our final solution.